Okay, for those of you just tuning in, and let's face it, if you're watching this, you're already part of the cool crowd. You're aware that I'm building an Enigma machine. A piece of cryptographic history, one piece at a time. So far, I've done the CAD dance, had some fun with the 3D printer, and machined the first part of the rack assembly on the lathe. In this episode, I'll transform this innocent-looking stainless steel bar into the next component, the rotor shaft holder. Before I start making a mess, I should explain what the rotor shaft does. It's buried deep within the machine. Right here, inside the rack assembly. In addition to supporting one end of the rotor shaft, the holder gives the lever assembly something to attach to. It also provides a bearing surface for the reflector. More about these parts in later videos. Complexity-wise, I'm heading into slightly murkier waters. The shaft has a small recess, about 4mm wide. A 5mm hole in one end, and a notch for the rotor shaft to sit in. There's also 3 mounting holes to contend with, which are trickier than they look. So here I am, messing with 316 stainless steel again. I just can't seem to get enough of this stuff. The stock is a bit on the chunky side, kind of like me after the holidays. The final part is 55mm long, so I have plenty to work with. The cutting tool of choice today is none other than the SW GCR 1212 EO5. Ah, the classics never die, do they? Ugh. Well, that doesn't sound right. Oh, I see what's wrong. That's more like it. Will you look at that? 2 microns. If you're wondering how small that is, a single sheet of paper is about 100 microns thick. An eyelash, 60 microns. Or, if you prefer imperial units, 47 200,000ths of a barleycorn. I'm kidding, of course. Instead, I'll use this old thing I had lying around. Much like the last Avatar movie, this part needs a lot of support towards the end. So a live centre to keep the part concentric is just the ticket. My part is about 22mm in diameter, and I need to slim it down to around 7mm. So I've got a few laps around the old machining track to bring it to size. Now, I've got a pizza in the oven, so to save time, I'm ramping up the aggression on the cutter. Well, that didn't work. Whose idea was this anyway? You know what they say, clearance is clearance. That surface finish is rougher than my grandma on a skateboard. Let's try this without the live centre. That's much nicer. Without end support, I'm going to have to take much lighter cuts, especially as the shaft gets smaller. Almost there. Bang on the money. Now that I've wrapped up the main shaft, it's time to tackle that inside shoulder. I'll admit, I got a little sidetracked with this B-roll of me operating the lathe, so I missed filming the actual facing operation. But mostly, it went like this. This was also a perfect chance to try removing the inside radius left by the carbide insert, using this carbide tool bit. I can't see a thing at this scale, so I'm mostly operating the lathe by feel rather than sight. For my next trick, I'll create this 4mm wide recess to fit the shaft of an M4 bolt. If I had a 4mm wide parting tool, this would be much simpler, but I don't. I do know, by direct observation, that this parting tool insert is 2.2mm wide. If I move this parting tool 1.8mm away from the first cut, I'll end up with a recess 4mm wide. I guess I need a few more subscribers before I can expect that to work. Until then, I'll part this off the old-fashioned way. It's time to deal with those end faces, which have had a tough day at the carnival. I'm just over a barleycorn long, which is easily fixed. And I'm punching a hole in the end with this 5mm drill bit. Here's the rotor shaft I made in the last episode. Let's see how it fits. That's good enough for me. It's time to bring out the big guns for the trickier features. The milling machine. In a way, it's just a lathe on its side, but slightly less likely to kill me. I'll tackle these 3 holes next. They look simple, but there's a catch. They're not equally spaced. If they were, they'd be 120 degrees apart. And I'd use this fancy 6-sided square block to drill them out one at a time. So I'll be using this, the rotary table. It's a precision ground plate that spins around a vertical axis, with a hand wheel controlling the rotation. Here's where it gets interesting. The ratio between the hand wheel and the table is 90:1. In other words, 90 turns of the hand wheel results in 1 full table rotation. That may sound like a lot of work to turn something just once, but because of that gearing, I have incredibly fine control over the angle of the table. It works the other way too. Turning the hand wheel once gives me 1/90th of a rotation of the table, or precisely 4 degrees. If you're switched on, and I know you are because your eyes are open, you'll have worked out that I can get the 130-degree angle for the mounting holes by turning the hand wheel 32.5 times. But now I have another problem. How do I turn the wheel by half a turn? Introducing the dividing plate. These plates allow the hand wheel to rotate by fractions of a turn. Engineers much more smarter than me have worked out how those fractions translate into table rotations. I'll dive deeper into how these work in a later video. For the purposes of this video, as long as I stick to these holes marked 20, I can pull off those half turns. Now that I've done a poor job of explaining how that works, I need to align the rotary table axis with that of the milling machine. I'm going to use this edge finder to find the inside edges of the rotary table. And then, using the DRO's half function, I'll find the centre of those edges. Did you spot the mistake? Have another look. Last time I checked, 13.67 isn't the same as 13.39. At least, not in this universe. Somehow I've introduced 280 microns of error in my measurement. Nonetheless, I'll carry on and pretend it doesn't matter. With the turny bit on the rotary table, now in alignment with the turny bit on the milling machine, I'm going to use this square collar block. There's a right way to mount this and a wrong way. Which way do you think this is? To get the collar block aligned with the milling machine, I'm using this 10mm gauge pin. After tightening the collet block, I can then tighten the clamps and remove the gauge pin. I'm now ready to mount the part in the collet. Before I can do this though, the machining gods need a small sacrifice. This brass spacer will do nicely, which also prevents me from drilling into the collet. It's no Antikythera mechanism, but it's perfect for what I need. There's a lot more brass coming in the next episode. A quick confirmation tap with the thumb detector ensures the part's seated correctly in the collet. That's enough setup. Let's do some drilling. I'll start with this center drill. And rotate the table around to 0 degrees. I move the milling machine by 7mm in the Y direction. Now, when I turn the rotary table, I can access all the positions required for the mounting holes. I swap out the tools, multiple times, for each hole. With that first hole down, it's time to give the hand wheel a turn. I then rotate the part another 100 degrees to reach the final hole location. What happens if I rotate the table another 130 degrees? I love it when a plan comes together. I finish off this operation with a quick single point countersink tool. I've only got 2 tool holders, so there's some unnecessary cranking here. It's time for my favourite part of the process. It's the "have I done a stupid" test. Does the part that I've been filming for the past 4 hours line up with its 3D printed doppelganger? I mean, it looks right, or at least right enough. That's the holes done, which leaves this last feature. Milling this flat bit for the notch. This looks like a simple operation. Mount it in the mill, and off I go. There's a plot twist, however. These mounting holes have to line up with the notch. There's a couple of ways I can do this. Whip up a single-use mounting fixture, 3D print some sort of alignment, whatchamacallit, or use the ichrometers. I'll use this 12mm roughing end mill. The first step is aligning the end mill with the end of the part. I can do this relatively accurately with this 0.5mm feeler gauge. I just move the x-axis until the feeler gauge stops moving. Zero the DRO, remove the feeler gauge, and then move the table 0.5mm back in the opposite direction. If the stars align, I should be right on the edge. The Z-axis is a very similar process, just at a 90-degree angle. Coming down 3.5mm and across by 5mm, I'm ready to go. After locking the house and ensuring the oven's off, I send it. It was at this moment that I knew I'd made a small transpositional alignment error. Those mounting holes that I drilled in what I thought was the centre of the part are in the wrong location. A quick check with the calipers confirms the error matches what I just saw on the DRO. But hey, I've come this far. There's no turning back now. A bit of deburring and a quick polish, and the part's done. Those mounting holes were drilled at 3.2mm, which, according to the book, the ISO 273 book that is considered a close fit for an M3 screw. This close fit gives the screw just enough space to fit in the hole, even with the error. Well, the part fits. That's half the battle won. Time for another flex test to see how it holds up. I'm not seeing much change here, but then again, I wasn't exactly expecting fireworks. The Achilles heel of this rack assembly still appears to be the plastic side supports. I'll tackle those in a future episode. So there you have it. My second, more complex, more shinier part. It's not perfect, but I like to think of it as having character. And sometimes that's enough. Thanks for watching.